Hello, good afternoon. We are doing chapter 12, part 2, so the last part. So I told you I'm going to derive a single slit in diffraction equation. Now let's talk about this guy over here. So we start from the center point. Remember, we have a wavefront that has an infinite amount of wave sources. They are made out of infinite wavelets. It's called the wavelets or the wave source. And only a certain number of wavelets gets passed through, right? We've talked about this. So what I'm left with is basically a number of wave sources. So 1, 2, 3, 4, 5, 6, 7. Let's just go with 7. So I have 7 wave sources. Like that's just an approximation because initially I had a wavefront made out of an infinite amount of wavelets or wave sources, and because I have to enter an opening, the opening only lets a certain part of the wave to pass through. So only a certain amount of wavelets gets passed through, right? Okay, so these guys passing through, they will diffract. And what do waves diffract do? They interfere with each other, and they interfere either constructively or destructively. So we know this part already. So how do we derive the equation for a single slit diffraction? So I'm going to pair, first of all, let's take a look on how to read this screen. So this is when we have a high intensity or when constructive interference happens. Constructive interference happens here, happens here, happens here, happens here, and happens here. And the part where the displacement is 0 or basically nothing is where destructive interference happens. Okay, forgive the handwriting. So this is destructive, 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 and destructive, right? So we know how to read this now. The part where it goes shallow is where you get destructive interference, and the part where there's an amplitude is where you have your constructive interference. Now, we already know that for a destructive interference to happen, the difference in path, the path difference between the two waves must be equal to half a lambda or half a wavelength, right? So if I were to pair these two waves, so this is my first wave, and I pair it with the midpoint wave over here. So that's a bad drawing. I'm going to use my shape, insert shape, and this will be my first one. So that's a blue. Do I not want to make it bigger? Maybe not. Okay, next one, and insert shape again. This guy over here. Let's go from the center. This is blue. Oh, okay, never mind. So I have these guys over here. So tak nampak pula. Sekejap. Let me format this to become thicker. So that's my first. And it meets with this guy over here. So that's the love story there. Right, so these guys, they interfere. These guys, they interfere with each other. And they interfere destructively because why? They meet at this point. Just bear with me with this story. Okay, let me put this bagi tepat sikit. Excuse me. Follow my instruction. No. Okay, that is where they interfere and destructive interference happens. And I told you it is very important for us to determine what is the path difference between these two waves because it decides whether it's destructive or constructive. Now, what is the path difference between these two waves? Let's draw that out as well. So let's use a different color for this one. So this is my path difference and I'm going to label this as green. Nampak tak? Bertebalkan. Okay, so that is my path difference. So draw. So this is my path difference and this is delta L. Remember delta L for constructive interference to happen. Why is my handwriting like that? So delta L, hello, focus. Delta L is equal to half a lambda if I want my destructive interference to happen, right? And we, in the Young's double slit experiment, we have figured out that sine theta, assuming this is theta, so that is a theta, let me, a second. That is a theta. This guy over here is a theta. Oopsie. Okay, so that is a theta. Let me use a different color. It's so bugging. Okay, so that's your theta. So we have seen that in Young's double slit interference, where sine theta is equal to delta L opposite over hypotenuse, which was over D. For this case, our sine theta is opposite, which is our path length. Okay, for this guy, sine theta is equal to path difference over, what is this guy? And I can't draw. Let me try again. So this is, what is this guy? This is actually A over 2. It's half the width of the slit. So A over 2. Now remember, what should the path difference be for destructive interference to happen? So delta L should be lambda over 2. So I'm going to plug that in. I can't write properly. I don't know why. Using it. Okay. So this is lambda over 2, A over 2. Okay. So now my 2 cancels out with each other. Great. So what does that leave me with? Leaves me with sine theta equals to lambda over A. This is my first equation. Great. Derive my first equation. The second one, I want my tangent theta because I want to relate this angle with the position of the fringes, right? So the position of my fringes is denoted by y, and we have derived this one as well in Young's double slit, which was tangent theta equals to opposite, which is y, and over adjacent, which is L. This is L, right? Okay, so this is y and this guy is L. So opposite is y and adjacent is L. Remember it. So this is your second equation. Remember, if your theta is infinitely, if your theta is super small or approaches 0, your sine theta is equal to tangent theta. And we already proved this. Use your calculator. Sine 0.001 is equal to tangent 0.001. Same thing. So here I can say sine theta is approximately equal to tangent theta. So what can I do with this information? Yes, I can equate it. I know. So it becomes lambda. I'm all over the place. Good job. Let me rearrange everything first. It's kind of hard to do that. Okay. Bring it up here. Okay, so we have tangent theta. We have sine. Theta. Get rid of this. So we have these two equations. I can equate them. Hooray! Let's do that. Draw black. Okay. So now I have lambda. Now I have lambda over A equals to y over L. So y dark, because this is for destructive interference, is equal to lambda L over A. But now I'm not done yet. Remember that our path difference should be a difference of lambda over 2. And it can be a multiple of it can be m lambda over 2, meaning it can be lambda over 2, 3 over 2, 5 over 2, and so on. So it's an odd half integer multiple of lambda. Odd half. Okay, so it's odd half integer multiple of lambda. So it becomes Now with this information, I'm going to revise my derivation. So delta L can be actually m lambda over 2, right? M lambda over 2. Okay, so this guy becomes m lambda, right? And this guy becomes m lambda L over A. It's m lambda over A, y over L, m lambda L over A. Have we seen this equation before? Yes and no. So this guy describes the fringes for a dark fringe. Gives you the position of a dark fringe. Gives you this position, this position, this position, this position. It looks like Young's double slit for a bright fringe. If you remember, let's take a look at the slide again. If you remember, Young's double slit says that, this is problems, where is the equation? Where is it? Hello. Cooperate with me, please. Where are you? Is it this one? No. Is this one? Is it this one? No. It's this one. No. Okay, so basically it's this guy. M L lambda over D. Looks familiar, right? This is for bright fringe, for Young's double slit. For the single slit, this describes the dark fringe. And it is m lambda L over A. The difference now is your D is replaced with the D, your D is replaced with the A, and this equation describes a dark fringe. Now I could go on and on deriving the same thing. I could extend this line with this line. It gives me the same angle, gives me the same equation, and I get the same outcome. And I can do this sampai habis until I interfere all the waves together. I will still get this equation. Now, would this equation, do I have an equation for bright fringes for a single slit diffraction? The answer is no. I do not have a y bright for single slit diffraction. An equation does not hold for a single slit diffraction. I cannot generalize it into an equation. Previously, for Young's double slit, we had, for bright, it was y equals to m L lambda over D, and for the dark, it was y equals to m plus 1 over 2 lambda L over D. Now, can I just add the 1 over 2 into this equation to make a y bright? The answer is no. It still doesn't work. So, kat sini, I want to emphasize that for a single slit diffraction, you only have a y dark equation to work with. So, pakailah macam mana pun, this is the only equation that you have for this diffraction, for this type of diffraction. Okay, so that is the derivation. Now, let's take a look at the equation to summarize sikit. So, position of dark fringe is given by ym equals to m lambda L over A. Remember, A is the width of your slit. The distance between the adjacent dark fringe. The distance between the adjacent dark fringe gives me the width of the central band. Okay, so this guy tolak this guy gives me the distance or the width of the central band. So how do I find that out? So I need to find out what is y1 minus y minus 1. Remember, this guy is the order number. So order number 1 and order number negative 1. Okay, so with that said, I know that my y1 is actually equal, the distance from the 0 to minus y1 is actually the same distance to 0 to y1. It's the same. This is y1, this is minus y1, ataupun y minus 1. The distance is the same. Now, if I can figure out what is y1, y1 is equal to m lambda L over A, and I know that the central band is basically 2 of the y1s, so I can just say it's just 2y1 or just 2m lambda L over A. This will give me the central band width. Okay, so distance between the dark fringes will give me the central band width. Okay, so if you are still not convinced, so let's use the equation. Let's say I have L that is equal to 1. Let's make this easy. D is equal to 100 nanometer, millimeter. D sudah. A is supposed to be A, it's not D. Okay, so A is that, and lambda is 570 nanometer, and I want to know what is my central bandwidth, right? And we know that central bandwidth can be found by finding out this guy. If you don't want to use this guy, you just want to use this guy. Okay, let's do that. It's fine. So y1, what is y1? y1 is equal to m lambda L over A, and my m is 1, lambda is 570, times 10 to the power 9, L is just 1. Let's make this easier. Let's say this is 100. Senang hidup aku. Okay, so that is 100. Walaupun ni bukan dalam visible wavelength. Okay, but just bear with me. Okay, so this is 100 times 10 to the minus 9 times 1. And our A is 100 times 10 to the minus 3. Semua dalam bentuk satu sahaja. Would that help with our situation? Yeah, I think so. Okay, let's do that. So my answer is, choose my calculator, 100 times 10 to the minus 9 divided by 100 times 10 to the minus 3. That's going to give me 1 nanometer. 1 times 10, 1 micrometer, sorry. 1 times 10 to the minus 6. So that is y1. What about y minus 1? What's the answer for that? Minus 1, 100 times 10 to the minus 9 times 1. Hello, tak cukup tempat pula. Do you get the idea? So, for y1, the answer was 1 times 10 to the minus 6. What's the answer for y? For an order of negative 1. The answer is the same, except that it's a negative. So let's let's write that down. Okay, so this is 1. Forgive the handwriting as usual. 100 times 10 to the minus 3. What do I get? It's a minus 1 times 10 to the minus 6. What does that mean? For y1, it gives me the distance between the center to position y1, position of dark fringe number 1. That is 1 times 10 to the minus 6. And here, it gives me the position of my minus 1 order of the dark fringe from the central band, from the center position. And it is at minus 1 times 10 to the minus 6. Or the distance is just 1 times 10 to the minus 6. So the width is just 2 times y1, right? So it's just 2 times y1. 2 times y1. And again, 2 times y1 is just 2m L lambda over A, where m is just 1. So it gives me 2 L lambda over A. So that is the same as this guy. So that is your width of your central bright band. Okay, lama cerita ni. Next one, let's do this example now. So we have two equations, the fringe, the y dark, right, for a single slit diffraction, and also the width of a central band. How do we find that out? y1 minus y minus 1, or just 2 times y1. Okay, it's the same thing. Okay, let's do this example. 12.6, a helium neon laser light with lambda 632.8 times 10 to the minus 9 is sent through a 0.3 millimeter wide. So that is times 10 to the 3. What is the width of the central maximum on a screen? 1 meter in the back of the slit. So the L is 1 meter. Meter. And kita nak cari width of central maximum. We know it's just 2y1. So 2y1 is equal to 2 lambda L over A. So that is 2 times 632.8 times 10 to the minus 9. 1 over A is just 0.3 times 10 to the minus 3. That is the answer. 2 times 632.8 times 10 to the minus 9 divided by 0.3 times 10 to the minus 3. So the answer is 4.21. 4.22 millimeter. Okay, so that's the answer. Next one, infrared radiation of wavelength 12.2 micrometer. So 12.2 times 10 to the minus 6 meter passes through a single slit, so a single diffraction problem. If the separation between the two first order minima, maksudnya y equals to 1, is 0.4 millimeter on a screen that is 84 times 10 to the minus 2 meter away. What is the width of the slit? It's asking what is A and what is theta? What is the diffraction angle? Okay. So how do we visualize this problem? So it's basically telling you there's so this is 0, this is y1, and this guy is y minus 1. So the separation between the two first order minima is 0.4. This is the separation. Okay, on a screen that is 84 centimeter away. So y1 minus y minus 1 is equal to 0.4 times 10 to the minus 3. Or we know that it's just 2y1 is equal to 0.4 times 10 to the minus 3. Okay, so that is the idea here. So let's use this information that we have. So y1 is just equal to, let me use a different color. Okay. Where should I write this? Okay, let's get rid of this guy over here because we already done it. Hello, goodbye. Okay, this one. Alright. Ooh, don't disappear, please. Okay. Okay, continuing. Okay. So I know that 2y1 is equal to that. So y1 is just equal to 0.2 times 10 to the minus 3 meter. What is the equation for y1? It's just m lambda L over A. So m is just 1, so I'm just not going to write that down. Lambda L over A, okay, equals to 0.2 times 10 to the minus 3. What is lambda? Lambda is given 12.2 times 10 to the minus 6. L is also given, it's 84 times 10 to the minus 2. A is unknown. The answer for that is 0.2 times 10 to the minus 3. So what is A? What is A? Using my trusty calculator, I figured out that A is 51.24 millimeter. 51.24 times 10 to the minus 3 meters. So that is my A. Now the question is asking what is the diffraction angle. So if we are talking between this guy and this guy, we are talking the distance separation between the two fringes, the two first order fringes, we are talking about this angle. That is our diffraction angle. Okay, so this is our slit and we are talking about that angle. Okay, so that is my angle. Kejap, patutnya dia dekat center lah sebab dia two first order slit, two first order fringe. Should be at the center. So this is my A. Okay. Alright, so I want to know what is theta. Okay, so remember sine. Oops. Okay, so I want to know what is theta, and we know that sine theta is equal to, from our derivation just now, from our derivation for a single slit, we had this equation. Sine theta was equal to lambda over 2 over A over 2. Remember the path difference, this was the path difference and this was A over 2 because we started from the midpoint. Path difference must be a multiple of lambda over 2, right? So that was our derivation. Command Y. Hello. It's not cooperating sebab saya dah mengajar lama sangat hari ni. Okay, thank you. Okay, so we can cancel that out. So we get this equation. It's lambda over A. We know this already. Okay, so from this one, we can find out the theta for this guy sebenarnya. We are actually finding out the theta for that guy. Remember, nanti saya tunjuk balik gambar dia. So if I were to solve the theta for lambda over A, it will give me a theta of 0.014 degrees, where lambda is 12.2 times 10 to the minus 6 and A is this guy over here. So saya akan dapat jawapan 0.014, but it is not this purple theta, it is this orange theta. Separuh je baru. So how do we find the purple theta? The purple theta is just 2 theta, which is equal to 0.028 degrees. Now, kenapa kita cari sin theta and boleh dapat jawapan untuk the diffraction angle? Now, let's take a look at our derivation balik. Wow, it's so messy. Okay, so why is it okay to use sin theta to determine this angle? Now remember, we had a path difference, right? This is A over 2. Let me besarkan kejap. This was A over 2. And this path difference had to be a multiple m lambda over 2 for destructive interference to happen. And we defined that this angle was theta, which means that this angle over here is also theta. And kita dah cerita how we got this theta in Young's double slit. It was the triangle should add up to 180, and then use your math, you will get that this guy over here is equal to theta. Okay, please go back to part 1 kalau tak ingat. So from that, if I solve for sine theta over here, if I solve for the theta over here, I'm actually solving for this guy over here. Now, what is the separation? What is the angle of diffraction between these two guys? Okay, remember the distance is the same. This part is also the same distance. So, basically they have the same angle. If I solve for sine theta, I am actually solving for this guy. How do I get the diffraction angle? The total diffraction angle, I times it by 2 because they are the same thing. They are the same value. Okay, so the diffraction angle for the diffraction angle between y1 with minus y1 or y minus 1 is 2 theta. Okay, I hope that answers the question. Okay, so now to summarize, a single slit diffraction has a has a central band maximum. This is given by 2y1. The equation is given by y dark. Okay, ym dark is equal to m lambda L over A. A is the width of the slit, m is your order number, lambda is your wavelength, and L is the distance from the slit to the screen. Okay. Your y will only give you the positions of, where is my pen? It's here. The positions of these guys, of these dudes. So if you want to find the central band, basically what you are doing is y1 minus with y minus 1. Remember, the one that is above the central band, the central point is positive. The one below this, the central point is a negative. So that is how we got the 2y1s. Okay. So here is they are showing you the intensity is it decreases as it moves away from the central point. Okay. For double slit interference, we had this equation y equals to, it's a m for bright, was m lambda L over d. D is the distance between the two slits. This gives you the position of the bright fringes. So if you want to find out what is the position of this guy, so you equate this guy with 0. So you get y0 as 0. So this is the position of your 0th order bright fringe. If you want to find out what is the number 1 fringe, so y1, 1 lambda L over d, and so on. So it gives you the position of bright fringes. Now, something to take note of is your m starts from 0, 1, 2, 3, and so on, plus minus, plus minus. For single slit diffraction, your m starts from plus minus 1. There's no 0. There is no 0. I need to emphasize this. There is no 0 for single slit diffraction. The order starts from 1. Okay. Now this is the intensity for a double slit interference. I told you it gets weaker as it spreads out. But here, the weaker part is not shown. So dia kena jauh lagi baru nampak weaker. But for the single slit diffraction, it's very obvious that the central band is like the maximum intensity, and then the rest of it is like just black, like that. Okay. So to summarize, this is the equation. Single slit diffraction is given by ym m lambda L over A starts from 0. And this is double slit interference, gives you start from 0. No, it starts from 1. Sekejap, saya check balik ni. And then for double slit interference, this is the equation, gives you bright fringes. This guy gives you dark fringes. Starts with m equals to 0, 1, 2, 3. Okay. Apa lagi nak summarize? The central band for a single slit diffraction is given by 2y1 central bandwidth. And for this guy, tak ada equation tu. Basically, they will just ask you to find what is the separation between this guy and this guy. Remember, if this guy is 3, this guy is also 3, this guy is also 3. The lengths, the distance are equal. This is not true for single slit diffraction. The distance is not the same at everywhere. Double slit interference, yes, the distance is equal. So y2 minus y1 will be equal to y1 minus y0 and is equal to y4 minus y3 as long as they are placed consecutively next to each other. Okay, I think that is it. Yep, that's it. All the best with your quiz and all the best with your finals. As usual, I'm available on your WhatsApp group or personal WhatsApp, whichever is more convenient for you, and take care. I'll see you around. Bye bye.